Hello everyone and welcome back to chemistry. Let me start with a question. Have you ever wondered why sodium, potassium, and lithium, though different elements, behave so much alike in chemical reactions? The answer lies in the way the periodic table is organized. In the modern periodic table, the vertical columns are called groups, and there are 18 such groups in total. What makes groups so important is that the group number directly tells us the number of valence electrons an element has. For example, every element in group 1 has exactly one electron in its outermost shell, while every element in group 17 has 7 valence electrons. Since the outer electrons govern how an element reacts, elements in the same group show strikingly similar chemical behavior. Think of the alkali metals, lithium, sodium, and potassium all react vigorously with water, producing hydrogen gas. If I write it down, the sodium atoms plus to water molecules give to sodium hydroxide molecules and hydrogen gas. That's written as 2Na plus 2H2O gives to NaOH plus H2 gas. So, groups are not just columns on paper, they are the key to predicting chemical reactivity. Now let's dive into our first group, the famous alkali metals. These elements, from lithium all the way to francium, are called alkali metals because their oxides and hydroxides are strongly alkaline in nature. Each atom in this group has an electronic configuration ending with ns1, meaning a single valence electron. For example, lithium is written as 2,1 and sodium as 2,8,1. Having just one electron to lose makes them extremely reactive. They are soft metals, can be cut with a knife, and must be stored under kerosene oil because they react instantly with oxygen and moisture in air. A classic reaction is their combination with halogens. Sodium, when reacting with chlorine gas, produces sodium chloride, common table salt. The reaction is 2Na plus Cl2 gives to NaCl. In everyday life, sodium chloride is the salt on our dining table, while potassium nitrate, another alkali metal compound, is used both in fertilizers and in fireworks. So the chemistry of alkali metals directly touches our food and our celebrations. Right next to them are the alkaline earth metals, that is, group 2 elements. They get their name because their oxides are alkaline and they occur abundantly in the Earth's crust. Their outer electronic configuration is ns2, which means they all have 2 valence electrons. For instance, beryllium is written as 2,2 and magnesium as 2,8,2. Compared to group 1, these metals are harder, denser, and slightly less reactive. But they still readily form ionic compounds. One beautiful property of magnesium is that it burns with a dazzling white flame in air, producing magnesium oxide. The reaction goes like this: 2Mg plus O2 gives to MgO. Magnesium oxide is a strong base. These metals also play crucial roles in our lives. Calcium carbonate, or limestone, is an essential raw material in cement manufacturing, while magnesium hydroxide, known as milk of magnesia, is used as an antacid to relieve stomach acidity. From groups 3 to 12, we meet the transition elements, also called D block elements. These are the strong, heavy metals of the table. They have partially filled d orbitals, and because of that, they display fascinating properties. They are hard, have high melting points, form colorful compounds, and often act as industrial catalysts. Take iron as an example. In its two oxidation states, iron 2 plus is pale green, while iron 3 plus is yellow-brown. These characteristic colors are due to their electronic structures. Beyond them lie the inner transition elements, the F block, which include the lanthanides from cerium to lutetium and the actinides from thorium to lawrencium. These elements are known for their unique properties. Uranium and thorium are radioactive fuels powering nuclear reactors, while lanthanides are used in making specialized glass and precision optical instruments. So, here, the periodic table literally connects chemistry to energy and technology. Jumping to group 17, we encounter the halogens. The word halogen means salt former, and rightly so, because these elements, fluorine, chlorine, bromine, iodine, and astatine, readily combine with metals to form salts. Their electronic configuration ends with Ns2, Np5, giving them 7 valence electrons. That makes them just one electron short of a stable octet, and hence highly reactive nonmetals. They exist as diatomic molecules, for example F2 and Cl2. One classic reaction is their displacement behavior. Chlorine gas, when bubbled into a solution of sodium bromide, displaces bromine because chlorine is more reactive. The reaction is Cl2 plus 2 NaBr gives to NaCl plus Br2. This shows the reactivity trend within the group. In daily life, chlorine is used in disinfecting drinking water, while iodine solution, known as tincture of iodine, is a common antiseptic applied to wounds. And then, standing majestically at the far right, are the noble gases, group 18. These elements are called noble or inert gases because of their complete outer shell. With the exception of helium, which is 1s2, all have the configuration Ns2, Np6. Neon is written as 2,8, argon as 2,8,8. This full configuration makes them extremely stable, colorless, odorless, and monoatomic gases. Because of their very low reactivity, they have some specialized applications. Helium is used in weather balloons and airships because it is lighter than air and non-flammable. Neon lights brighten up shop signs in glowing red-orange colors. Argon, being chemically inert, is filled inside incandescent bulbs to prevent the hot filament from reacting with oxygen. So, noble gases remind us that even the most silent elements have essential roles in technology. Now let's step back and see the bigger picture, the trends that emerge as we move down a group. First, the number of valence electrons remains exactly the same, which is why the chemical properties within a group remain similar. However, as we move down, the number of electron shells increases. This means the atomic radius becomes larger. With a larger size, the outer electrons are held less tightly, and hence, metallic character increases down a group. Take the alkali metals for instance. If I ask you, which is more reactive, lithium at the top or cesium at the bottom? The answer is cesium because with more shells, the single valence electron is lost more easily. So, trends in groups not only explain periodicity but also help us predict which elements are more reactive or more metallic as we move downward. So, let's quickly recap. Groups are the 18 vertical columns of the modern periodic table. The group number tells us the number of valence electrons and therefore the reactivity of elements. We explored how Group 1 Alkali Metals and Group 2 Alkaline Earth Metals are highly reactive, how transition and inner transition metals form colorful compounds and act as catalysts, how halogens in Group 17 form salts and disinfect our water, and how noble gases in Group 18 stand out for their stability and useful applications. We also saw that as we move down a group, the atomic size increases, metallic character strengthens, and reactivity changes systematically. I hope this session helped you see that groups in the periodic table are not just arrangements of elements, but a powerful tool to predict the behavior of matter in our daily lives, in industry, and even in advanced technology. Chemistry is truly the language of the elements. Catch you in the next class with more fascinating insights into the periodic table.